Yeah. Welcome to the last recitation. Yeah, cool. Awesome. Yeah, we're ready for this. All right, so if you have the exam key, skeleton key with you, we're probably just gonna do, a problem from each of these, so like one for one. I don't think there's any that will. Yeah, I don't think we'll skip any. Well, any of them that say concept problem. Yeah, sorry, I have no idea what he's gonna do. Although I will be there to proctor the exam because I don't think he's gonna be there. So I'll be there. If you have questions, hopefully I'll know. Sorry if I
He
don't.
doesn't trust us.
Yeah.
He'll be right upstairs though. Like
Which
he's just
is,
giving
valid.
he's just giving a presentation, so it's not a big deal. If we have to ask a question. So the first question on skeleton key is from almost over 2 weeks ago now, where we have 3 layers of different in values, and
That's a throwback.
yeah, I know,
Throwback.
isn't it? And we need to find the minimum thickness of this layer, this middle layer, in which you'll have constructive interference. So remember, if in top is greater than in bottom, there's no flip. But if it's the opposite, so in bottom is greater than in top, then it'll flip. Okay? So for instance, if we were asking if the light from this, which we could say is like air, so n equals 1, hits this and reflects off, and it was a crest when it came and hit it, it would flip to a whatever the other thing is now. I can't even remember. Trough. Thank you. Trough. Yeah. Crest to trough. So higher to lower, it would not flip. It just stays the same. And when you're just passing through a layer, so like here, when you're just passing through and not reflecting, you don't worry about it. It does not flip in those instances, only when it's reflected. Okay, so for this problem, I'm giving a frequency of 5 times 10 to the 14th hertz, which we need to change to a wavelength. So, which I think is something like,
F equals CD.
I think it's like 400, but I can't remember. So yeah, what'd you get? 600 nanometers? Okay, perfect. So that would give us a wavelength of 600 nanometers.
How did you get that?
That's just the C equals F, frequency times wavelength. Okay. So basically we just need to know the thickness of this layer that'll give constructive interference. So we need to also know the wavelength in this layer, n equals 1.5. So all you have to do that is just do 600 divided by 1.5 will give you the wavelength in the material. Okay, so the wavelength in 1.5 just equals 600 divided by 1.5. 400, which equals 400 nanometers. Okay? Cool. So from there, we use this interesting equation, which is the, oh crap, I have no room. There it was.
Is it always the middle end that we are
Yeah, that's what it should be.
Okay.
Yeah, it should be the middle one. That's what we did in homework, so I'm assuming it's gonna keep the same. But I mean, you could do it for probably all of these, probably. But the middle one's the most reasonable because then you can have reflections and flips and stuff. So this is not the full equation, which I need to remember what the full equation was. Sorry. I forget things too. And Or is that the entire thing? Oh, equals 2t. Okay, that was it. Equals whatever times 2t. Okay, sorry. That's it. Okay, so total path over wavelength equals x, which is basically the number of wavelengths that we're wanting to get. So for the thinnest, the thinnest of this layer that we can have that will give us constructive interference, how many wavelengths is that?
In phase or not?
In phase. It should be in phase. Yeah, they started in phase.
How do you know?
Hills, if he doesn't say out of phase, they're always in phase.
What do we do differently if they're out of phase?
If they're out of phase, they shift by half. So here, let me go over it. So, so for constructive, the thinnest that you can possibly have, this x value will be 1. And then it just goes up by whole numbers. So then the second thinnest would be 2, third thinnest would be 3, and so on. Okay? And then and then if he was asking for destructive interference, it would start at half, at 1/2, because that'll be destructive, and then it'll go up by whole numbers again. So 1.5, 2.5, etc. But if he says they start out of phase, then those two number sequences switch. So for constructive, when they start out of phase, the thinnest that you could have is half, is 0.5, and then 1.5 and 2.5. And the opposite for destructive. Destructive would start at 1 and go to 2 and 3, and so on. Okay, so for this case, it's in phase, and we want the thinnest possible. So therefore, it's 1. This x value is 1. And then we always have 2t. So we are looking for the total path. Yeah. Okay. So let's see. Wavelength is 400. I have absolutely no room because I have Fusion already. So total path. Equals 1. 2 times the thickness. So that means the total path that it's going to take, if we just multiply this over, will equal 400. So which equals 2 times the thickness. Okay, and what we're looking for is thickness, so all we have to do is divide this 400 by 2, and we get t equals 200 nanometers. Okay? Is everybody good with that part? Okay, cool. So let's just say if we did a different way and we started in phase, but he wanted the second thinnest layer that you could have that gave destructive interference. What would you have this number be?
1.5.
1.5, exactly. So if you put that into this equation, you'd multiply 400 times 1.5, divide it by 2 again, and you'd end up with like 300. I think it's 300, yeah. So that's how you do this every single time. Just use this equation. The only thing that will ever change is this x value. And remember, this is the wavelength in the medium. Okay, so the second question is, in the same problem, what is the second largest thickness that gives destructive or constructive interference? Which we basically just did conceptually, but I'll actually do, not sharp laser. So, but we'll actually do this again. Okay, so let's say it is destructive and it's, well, we already did that. So how about we say it starts out of phase? Let's just see, kind of goes a little off of this. So let's say it starts out of phase and he now wants the second thickness that's destructive. Second thickness, destructive, and starts out of phase. What is the number? 2, exactly, okay. So normally constructive would be whole numbers, but since they start out of phase, destructive will be the whole numbers, and the second thickest is obviously 2. So if we have these same numbers and we just work this out, you'll end up with 800 equals 2t, and then t equals 400. Okay. Are there any questions on this type of problem?
Are we looking at when we divided lambda or the 1.5? Are you looking at the dotted line or are you looking at the both of them?
It'll be this dotted line, yeah. So this is, it's this thickness.
Okay.
Yeah, we're asking if these are in phase. Okay, so, oh, I completely forgot crest and troughs. That's great.
The switch.
Yeah, I forgot the switch, guys. Okay, but, so let's go over that. So that was if there was no switching. So that's great. So now we have to do if there is switching. So let's say it starts with the crest here. So now we have to decide if things flip or not. It's going to be fun. So at this layer, we have an n that's greater than the one up below. So does it flip or does it not flip? It does not flip. Okay, so there's a crest again. Okay, so now we're going down here. So now we have 1.5 over 2. Does it flip or does it not flip? Okay, so it started with a crest and ends with a trough. And then that means up here will also be a trough. So basically this means that this is a situation in which you'd start with those out of phase numbers, okay? So if you draw your diagram out like this and you decide this is a crest and this is a trough, that's where you can basically say that your light starts out of phase. And that's when you use those out of phase numbers where constructive interference will be half, 1/2, and 2.5. And then destructive will be whole numbers, 1, 2, and 3.
So they're different things at
yeah.
this point than that's destructive?
Yeah, so if we started the equations like this, basically, so now we'd have to say that this is starting out of phase. So if we're saying they start out of phase, and the first question once again asked, what is the minimum thickness that gives constructive interference? So what number do we use if they start out of phase and we want the thinnest possible?
0.5.
0.5, exactly. So once again, just put the numbers in there like you need to. Yeah, 0.5. And so you'll end up with 200 equals 2t, t equals 100 nanometers. Okay, does everyone understand that? Now that we added flips, yes, Claire?
Yeah, so are we doing it like now that it's flipped?
Yeah, we're doing it now that it's flipped. So basically, if we weren't paying attention to any of the flips and they were all, so let's say this was like, let's say that this was thicker than this and this was thicker than this. So these had higher values going from top to bottom. So this is highest and this is lowest. In that case, there's no flipping, and you automatically know that they should both be crests when they're meeting up again. And this is the point where you're wanting to know if they're in phase or out of phase to start with, okay? Yeah. So if we had a situation where, let's say, this is 1, this would no longer flip, and you'd start here, you'd have this as a crest. So that's the situation I just described. So that's in a situation where the light is then in phase, and you start with the in phase numbers, okay? Are we good with that? Are we not good with that? Looks like most people are saying yes. Okay. If you have questions that you don't want to ask right now, you can stay later. Okay.
Well,
So
is he going to give us that picture?
yeah, he'll definitely give you a picture. Yeah. Yes.
Is he going to say that it's in phase or out of phase, or do you decide it?
I think he's gonna say, well, he's probably gonna say you just have a light, and then you'll have to decide if it's in phase or out of phase.
Based on the flipping?
Yeah, based on the flipping. Yeah. Yeah, there shouldn't be anything that. Yeah, it shouldn't like start out of phase, and then you'll have to decide if it goes in phase. That doesn't really make sense. So it should start like this, and you'll have to decide if it's in or out. Okay, I'm gonna go on the next one. Okay, so there's an additional concept question 3. On wave interference, and I don't know what that's gonna be. I have no idea. He's weird. Okay, so the next thing is a photon of wavelength, blah blah blah, illuminates a metal surface having a work function of something, and the kinetic energy in electron volts of an electron ejected is what? So there's a good equation which I believe is just energy equals KE, but I probably didn't write down. I got it. Here it is. Okay, yeah, so KE max. So, okay, here's the equation that you need for that. It's KE max, which it's always going to be max, equals HF minus some work function. Okay? So remember, when he's talking about this, it really doesn't matter what the amplitude of like the light rays or whatever he's putting on there is. It's basically only the frequency. So a higher frequency will be a higher energy photon. So if he gives you, let's say he gives you a frequency just like we had last time. So let's say we have a frequency which is 5 times 10 to the negative 14th hertz. And then Planck's constant is H equals 6.63. H equals 6.63 times 10 to the negative 34 joules times seconds. Okay, I'm gonna have something that's a really small work function. Okay, so we have a really small work function. So to do this, we basically need to just multiply H times F and then turn this from joules to electron volts, because H is always in joules. So to do this, we're going to do KE equals H, so 6.63 times 10 to the negative 34 times 5 times 10 to the, not negative, sorry, I don't know what that thing, times 10 to the 14th. And then divide this by the conversion factor, 1.6 times 10 to the negative 19th joules per electron volt. And then subtract the work function. That's all we gotta do. You know what you guys get to 2 decimals. If you do. What? 1.57? Yeah, awesome. 1.57, yeah, that's what I got. So the kinetic energy of the electron that gets ejected will be 1.57 electron volts. That should be what he keeps it in, as electron volts. Yep, in electron volts. So yeah, that's all that problem is. Does anybody have any questions with that one? That one's pretty simple. You literally, yeah, just a lot of these are making sure you know the right equation to use, which is like half of physics. So yeah, make sure you know the equations. This is the one you guys did, so I'll erase.
Do you want me to pause it? Or start another one?
Yeah, might as well. It's gonna be long if you don't.
No.